Hi, Assalamualaikum warahmatullahi wabarakatuh, my dear students. Madam Ruby again here. I am going to talk about the last chapter in our organic chemistry, amine and amino acids. First, lesson 81 is talking about the structures, basicity, and how to prepare amine. We have to name amines and classify them, explain the physical properties, boiling point, solubility, comparing the basicity between ammonia, aliphatic, and aromatic amines in terms of inductive effect of substituent groups and resonance effect. Then we're going to prepare amines by reduction of nitro compounds, nitrile compounds, and amide compounds. We also can produce amines by using Hoffmann's degradation. Amines are one of the derivatives from ammonia. Look at ammonia compound here. It has 5 electron valence. It has 1 lone pair on top. So the geometrical shape would be what? Trigonal pyramidal. Good, you remember. So having the lone pair, making it basic and also nucleophilic, meaning it's going to act as nucleophile. Amines are classified into 4 categories: primary, secondary, tertiary, and quaternary. How do we know which one is primary? By having only one R attached to the nitrogen. And the secondary amine would have 2 R. Tertiary amine would have 3 Rs. This is a quaternary amine where we also called it ammonium salt, because it has 1, 2, 3, 4 Rs, and it is bonded ionically with a type of metal salt. In your page 360, we have come to the end part of the book. Let's revise the name of amines and their classification. Compound A is a 1-propanamine. You don't even need to write number 1. We can just write propanamine. Yes, it has 3 carbons. It is a primary amine. The second one is a methyl group attached to N, an ethyl group attached to N. So ethyl is the longest chain. We are naming it ethanamine. So a substituent is attached to N. So N-methyl ethanamine. This is a secondary amine. C, we have 3 Rs. So this is a tertiary amine. We have 1-methyl, 2-methyl attached to N. So N and dimethyl ethanamine. This tree is categorized as aliphatic amines. These 3 compounds are aromatic amines because they have benzene ring attached to it. So let's do D. D has a methyl group attached to N. NH2, if attached to benzene, is called aniline. So we put methyl as substituent attached to N. So the name for D would be N-methyl aniline, which is a secondary aromatic amine. Aniline is a primary aromatic amine. And E, we have methyl and ethyl attached to N. So we mention ethyl first because it is according to alphabetical order. E is tertiary aromatic amine. In your book G, that would be cyclohexanamine. Next, we're going to look at boiling points of amines. Amine has nitrogen. Nitrogen is an electronegative halogen which can form hydrogen bonding with hydrogen. So, comparing amine to alkane, amine can form hydrogen bonding, so the boiling point would be higher compared to alkane. Alkane only has weak van der Waals forces. But if we compare amines with alcohol, alcohol will have higher boiling point because of the electronegativity of oxygen is higher than nitrogen. So if we look at the increasing boiling points here, alkane, it has van der Waals forces. Amine has hydrogen bonding with N. It's lower than alcohol because oxygen has higher electronegativity compared to N. Carboxylic acid would have a higher boiling point because it has the structure of dimer. For one compound, it can form as much as 2 hydrogen bonding between each other. Now, among the classifications of amines, the boiling point would differ because tertiary amine would have no hydrogen bonding because it doesn't have hydrogen attached to its nitrogen. In order to have hydrogen bonding, the nitrogen must have a free hydrogen attached to it, a free proton attached to it. So primary amine would have a lot of hydrogen bonding among the molecules because of the electronegativity part of nitrogen having the lone pair, and then an available free hydrogen here, 1 and 2. But secondary amine would have a lower boiling point because it can form less hydrogen bonding compared to primary amine. So you have to compare all of this between compounds that have similar molecular weight. Okay? So in conclusion, we would have a higher boiling point for primary amine because it can form more hydrogen bonding compared to secondary amine, but tertiary amine cannot form any hydrogen bond at all, so it has lowest boiling point. Now let's look at the solubility of amines. Since it has hydrogen bonding, yes, it can be soluble in water. It's just that when the number of carbon is bigger, the hydrophobic part of the organic compound amine is going to be more difficult to be soluble in water as it is big. Okay, we know acidity is the ability of a compound to donate hydrogen. But basicity is the ability of a compound to donate electron. So amine having a lone pair, it actually can make bonding or bondage with hydrogen or a proton. So an ammonia can react with water to form an ammonium ion. Means that it is basic. Right, let's look at the inductive effect of an EWG and EDG group upon basicity of certain amines. If we have an electron withdrawing group, that group will be attached to amine and it will attract the electron from the alkyl ammonium ion. So the electron is less available to be bonded with proton, hydrogen. So this makes the alkyl ammonium ion unstable, hence decreasing the basicity. But if we have EDG, electron donating group, it will be attached to the amine and donate its electron. So the positivity of the alkyl ammonium ion would increase and making it more stable, increasing the basicity. In short, we can say that, for example, an alkyl group, it's an electron donating group. It will stabilize the alkyl ammonium ion by adding more to the positivity of charge. So the larger the alkyl group, the larger the effect of electron donating, the more stable would be the ammonium ion, making it more basic. Next, let's look at resonance effect. For this part, we have to know that aryl amines or aromatic amines would become a weaker base because it has 4 resonance structures compared to aliphatic and cyclic amines. Cyclic amines is, for example, our cyclohexanamine just now. So why is that so? The lone pair electron from the nitrogen would go inside the resonance structure of the aromatic ring and delocalize within the ring. So it is less available for bonding with proton from outside. Let's look at the 4 resonance structure. Okay, this is the first one. As you can see, the electron lone pair will go and move into the ring, and the double bond inside the ring will move to the next carbon, like this. Okay. And then the negative charge here will make the double bond become single, okay, like this, and it will move so that the double bond becomes at the opposite side of the benzene ring, like this. The negative charge now is at carbon number 4. Then it will move again to its adjacent carbon and will make the double bond move to the next carbon as we have shown here. So again, the negative charge moves. So the electron from the lone pair of nitrogen is going to move around inside the benzene ring all the way, all the time. So this will make aryl amine more stable. So hydrogen from outside is not available to be bonded with nitrogen here because the electron is used inside the ring. Now, what is the effect of EWG and EDG on an aryl amine? So, the same effect, inductivity, is going to happen on the aniline because an EWG, electron withdrawing group, will attract electron from the positive charge of ammonium ion and destabilize the aniline, making it decrease the basicity. So as EDG here will give its electron to the aromatic ring. So the electron lone pair will be attached towards the positive part of the ammonium ion, making it stable, so it will increase the basicity available to bond with hydrogen from outside. Let's do question number 6. in tutorial of this chapter, arrange the following compounds in order of ascending basicity and explain. We have to arrange these 4 compounds. So what are their classifications? Ammonia, methanamine is primary aliphatic amine. This is aryl amine. This is an amine which is aromatic and has an EWG. Electron withdrawing group. How do you know it's EWG or EDG? You can look at page 232 in chapter 6 benzene. Remember table 6.3 listing the meta, auto, para when we are doing effects of orientation and reactivity on benzene ring. So EWG would destabilize the ammonium ion as it withdraws the electron that is delocalized in the benzene ring. So this compound, para-nitroaniline, would be the one that has the lowest basicity. It would be on the far left here. And then followed by aniline, because aryl amine has a weaker basicity compared to ammonia and aliphatic amine. Ammonia is number 3 here. The highest basicity is for methanamine because EDG or methyl is attached directly to N, where it will give an inductive effect whereby EDG would donate its electron, so the electron is more available to be bonded with H. Okay, arrange the compounds below in order of increasing Kb value. So you need to revise what we have done in chapter 7, Sem 1. What is Kb value? The higher the Kb value, the higher or stronger the basicity of a compound. It's a constant to measure basicity, the concentration of OH minus, or the ability of the electron to be donated. Okay, so we need to arrange by increasing basicity lah. Okay. The lowest basicity would be the aromatic ring would have EWG attached to it. Which one is EWG? Yes, this one, NO2. So this would be on the left here, number 1. Okay. After that, increasing basicity would be aniline. Aniline would be number 2. And then after that, we have an EDG, electron donating group, a methyl group attached to aniline, because ethyl group will donate its electron into the benzene ring so that the electron at the nitrogen would be available to be bonded with hydrogen from outside. So the basicity increased because it's more stable. The ammonium ion is more stable. So this compound would become number 3. Okay, it's the second highest. The highest would be this one. This is a cyclic amine. This is a cyclohexanamine. It has the highest basicity in this question because it is not a cyclic compound. It is not an aryl amine. Let's look at preparation of amines now. In your page 381, you need to fill this information in the top left of that page. And we're going to use haloalkane as raw material and react it with ammonia ethanol reflux to form amine. Okay, the second part would be Nitro, Nitrile and amide compounds. Reducing agents, any of these 4 would be used to form amine. And the third one is, this is an amide as well, but the reaction here is called Hoffmann degradation. Why do we call it degradation? Because 1 carbon will be eliminated. So it's going to form an amine which have less one carbon compared to the reactant. Okay, we have done this reaction previously in chapter 7, haloalkane. Let's just revise. This is the first box in that page of your mind map. Haloalkane is going to react with ammonia in ethanolic solution and heat to produce a primary amine. Having excess ammonia is going to stay as primary amine, but if you have a limited ammonia, the product is going to react with the primary amine here and it will become secondary amine. And if we don't have excess ammonia, also we're going to produce tertiary amine when the product reacts with secondary amine. So this is actually a propagation type of reaction. Okay, let's do example 11.1. Question number 1, we have chloromethane. It reacts with excess ammonia in ethanolic condition. Reflux is going to form a methanamine, a primary amine. Okay, second question, this is chloroethane. Reacts with methanamine, the one that we produce here. And we will form secondary amine. The secondary amine is named N-methyl ethanamine. Question number 3, chloroethane reacts with N-methyl methanamine to form tertiary amine, which is going by the name N-dimethyl ethanamine. And finally, chloroethane reacts with a tertiary amine to form this quaternary amine. This is an ammonium salt derivative. The second reaction we're going to do is reduction of nitro compounds. Nitro compound is RNO2. Here, oxygen in nitro group is going to be reduced to become NH2, amino. So we're going to use any of these 4 reducing agents. You're familiar with all these 4. We've been using this since carbonyl chapter, carboxylic chapter as well. Fill in the example 11.2 now. Question number 1. This reactant is going to be reduced to produce a propanamine. And this nitrobenzene is going to be reduced to produce aniline. The third reaction would be reduction of nitriles. Nitriles is RCN, the one that we have done in chapter 7 haloalkane, where we produce nitriles from haloalkane using one of these reducing agent. The one that we learned is H2 gas, Ni, PT, PD, heat. But we actually can use other 3 also. Bear that in mind when you are doing exercises in chapter 7. So we are going to produce an amine here. Example 11.3, let's reduce 1 cyanopropane to become 1 butanamine. You can see here, notice that the number of carbon is increasing by 1 from the original haloalkane that we used to form this nitrile compound. Second question, cyanobenzene. We reduce this compound to form phenyl methanamine. The fourth is reduction of amides. As you remember, we have formed amides during the formation of carboxylic acid derivative, the last derivative that we've done in lesson 79 last week. So we're going to remove the double bond O at the carbonyl carbon, and we are going to produce an amine. The reagents are the same, any of the four reducing agents. Example 11.4, question number 1. This is a butanamide. We are going to remove double bond and oxygen. We are going to produce one butanamine. Second question, this is a phenyl methanamide. And we are going to remove double bond O. We are going to get a phenyl methanamine. The most interesting reaction that we're going to do to prepare amine is Hoffmann's degradation. Why? Because we're going to remove C double bond O, the carbonyl compound, altogether. We're going to use X2, it's either Cl2 or Br2. Basic environment, so we're going to put sodium hydroxide or potassium hydroxide with water, and we're going to form an amine together with a carbonate ion. So the elimination of a carbonyl group will make the length of the carbon chain shorten by one carbon. Let's do example 11.5, question number 1. We have 2 phenyl ethanamide. So we are going to remove C double bond O and form phenyl methanamine. So notice that from ethanamide, it becomes methanamine. We lose one carbon there. Question number 2 is 4 phenyl butanamide. So we're going to lose that C double bond O and produce 3 phenyl propanamine. Thank you very much for watching and listening to me. This is the last moments of us together in lecture. So bear with me just for a little bit and you would be excellent in organic chemistry. Thank you. Assalamu alaikum warahmatullahi wabarakatuh.